let's learn about acid-base reactions. Now there's all kinds of ways to classify acids and bases. There's Arrhenius acids and bases, there's Bronsted-Lowry acids and bases, there's Lewis acids and bases. For our purposes, we're going to stick with Arrhenius acids and bases. An Arrhenius acid is any compound molecule that when you dissolve it in water, it increases the hydrogen concentration in the water. That's H+. H+ is a positively charged ion. We call it a cation. So a common example would be household vinegar. This molecule has hydrogen right here, and this hydrogen can dissociate from the molecule when it dissolves in water. And so it's this hydrogen floating around in the water that makes something like vinegar an acid. And then there's Arrhenius bases. An Arrhenius base is any compound or molecule that when you dissolve it in water, it increases the hydroxide concentration in the water. Hydroxide's formula is OH. It's what's called a polyatomic ion. It has a formal charge of 1-. A negatively charged ion is called an anion. So a good example is sodium hydroxide. Sodium hydroxide is a compound that has a sodium ion over here and a hydroxide ion over here. When this dissolves in water, the hydroxide ion goes off, dissolves into the water, and increases the hydroxide concentration in the water. So, keeping in mind that this is the definition of acid and base that we're working with, Arrhenius acids and bases, let's head into the lab and do an acid-base reaction. I'm going to demonstrate for you an acid-base reaction. Acid-base reactions come in all kinds of different versions. This particular acid-base reaction is a type of double replacement reaction. And that's usually the case when you're dealing with what's called an Arrhenius acid and an Arrhenius base. So in this acid-base reaction, I've got an Arrhenius acid, that's hydrochloric acid, HCl, and I also have an Arrhenius base, and that is sodium carbonate, more commonly known as baking soda. Now, to really illustrate what's going on in this reaction, I'm going to add a little bit of indicator. This indicator is called phenol red, so I'm going to add that to my vessel here. An indicator is a compound that changes color in different pH environments. So the first thing I'm going to do is add my base to this vessel, and we'll see what happens here. So I've added my sodium bicarbonate solution to the indicator, and we can see that it has remained red. So this indicator is a pretty rosy red when it's in a basic solution. So now I'm going to add my hydrochloric acid, HCl. So here we go. I'm going to add my hydrochloric acid. We see a few things going on right away. So you should have noticed two major changes here. Probably the most notable one is that we have a striking color change. The indicator changed from red to this pretty yellow amber. That indicates that the pH changed. That makes sense. We added an acid to a base, so we would expect that solution to change its pH. We also have the evolution of a large amount of gas. Now, a moment ago I told you that many acid-base reactions resemble double replacement reactions. So with that in mind, I want you to think about what might have happened in this reaction. If I combine my sodium bicarbonate solution, that's my base, with hydrochloric acid, I see a change in the pH, and I also see the evolution of gas. What products might have been created in this reaction? So the acid-base reaction we just saw in the lab was a pretty interesting one because it generated carbon dioxide gas as a product. That's not always the case. In fact, it's really not characteristic of acid-base reactions. It's just kind of an interesting one to look at. But that reaction we saw between hydrochloric acid and sodium bicarbonate might look a little bit like this. Over here, we have the hydrochloric acid, and here is our sodium bicarbonate. The hydrochloric acid produces a bunch of H+ ions floating around in the solution, and the sodium bicarbonate produces a bunch of hydroxides floating around in the solution. These hydrogen ions and hydroxide ions find each other in the solution, and they produce water. So for a reaction between an Arrhenius acid and an Arrhenius base, you always get water as one of the products. If we look at what's left over in the reaction, we have sodium ions and chloride ions floating around in the water. So one product of an Arrhenius acid-base reaction is also a salt, such as sodium chloride. That's common table salt. The reaction we saw in the lab had carbon dioxide as a byproduct, which actually left the system. That's why we saw the formation of gas, all that fizzing in the Erlenmeyer flask. That fizzing gas was a little bit of a fun bonus in that reaction. So that's a couple of good examples of acid-base reactions with Arrhenius acids and bases.